Welcome to Learning Outcome 3, all about heat and how it affects gases, liquids and solids. We'll look at temperature and how we measure it, the ways heat travels, the gas laws, and what happens when a substance changes state. Let me sketch out the journey ahead. We'll see how temperature is measured and why engineers keep two different scales on the go. We'll meet the three ways heat gets around: conduction, convection, and radiation, and the gas laws that describe how gases respond to pressure and temperature. Then we'll work out how much heat it takes to warm something up using Q equals mc delta T, and how much it takes to change its state using Q equals ml. And throughout, the skill is picking the right law for the problem in front of you. Let's clear up a common confusion straight away. Heat and temperature are not the same thing. Temperature tells you how hot something is. Really, it's the average kinetic energy of the particles. Heat, on the other hand, is energy on the move, flowing because of a temperature difference, and it always travels from hotter to colder. We measure heat in joules, but temperature in degrees Celsius or in Kelvin. Think of a spark. It's blisteringly hot but carries very little heat, whereas a warm bath isn't that hot yet stores a great deal. Let's define a few terms. Temperature is a measure of the average kinetic energy of a substance's particles. Heat, or thermal energy, is the energy that flows from a hotter body to a colder one, measured in joules. Thermal equilibrium is the state two bodies reach when they've settled to the same temperature. Absolute zero is the coldest temperature possible, 0 Kelvin, or about minus 273.15 degrees Celsius, where particle motion is at its absolute minimum. And the Kelvin is the SI unit of temperature, with each Kelvin the same size as a Celsius degree. Let's compare our two scales. Celsius pins 0 degrees at the freezing point of water and 100 degrees at its boiling point. Kelvin instead starts right down at absolute zero, the coldest anything can get. To go from Celsius to Kelvin, you add 273 or 273.15 for careful work, and to come back, you subtract it. Because the degrees are the same size, a change of 1 degree Celsius is exactly a change of 1 Kelvin. And here's the golden rule. Always use Kelvin in the gas laws, never Celsius. Let's practice converting. A workshop compressor takes in air at 25 degrees Celsius, and we want that in Kelvin. Adding 273 gives 298 Kelvin. Its outlet, meanwhile, reaches 348 Kelvin, and we'd like that back in Celsius. Subtracting 273 gives 75 degrees Celsius, so the inlet air is 298 Kelvin, and the outlet air is 75 degrees Celsius, the same physical temperatures, just written on the two different scales. Heat gets from place to place in three ways, and it's worth being able to tell them apart. Conduction passes energy from particle to particle through a solid. Think of a metal spanner slowly heating up. Convection carries heat in a moving fluid. As warm fluid rises and cooler fluid sinks to take its place, like the water circulating in a boiler. And radiation carries heat as infrared waves that need no medium at all. That's how warmth reaches us from the sun or the face of a furnace. Metals conduct well, while gases are poor conductors and so make good insulators. Let's put conduction and convection side by side. Conduction happens mainly in solids. The particles stay put and simply hand the energy along. And metals do this especially well thanks to their free electrons. Heat travelling along an engine bracket is a good example. Convection happens in fluids, liquids and gases, where the fluid itself physically moves and carries the energy with it, driven by the density differences that heating sets up. The coolant circulating around a car radiator is convection in action. Let's give radiation its own moment. Radiation is heat transferred by infrared electromagnetic waves, and it's the only mode that can cross a vacuum, which is exactly how the sun's warmth reaches us across empty space. Surfaces matter here. Dark, matte surfaces are good at both emitting and absorbing radiation, while shiny, light surfaces reflect it and emit poorly. Engineers use that knowledge deliberately: silvered heat shields to reflect it away, matte black fins to radiate it off. And in any real system, remember, all three modes are usually at work together. Now to the gas laws, starting with Boyle's law. At a constant temperature, the pressure and volume of a fixed mass of gas are inversely related. Squeeze the volume down and the pressure climbs. Let it expand and the pressure drops. We write it as pressure times volume equals a constant, so the pressure times volume before equals the pressure times volume after. You reach for it whenever temperature and mass are both fixed. Compressing air in a pneumatic cylinder or a bicycle pump, say. Just keep your pressures and volumes in consistent units. Let's apply it. We have half a cubic meter of air at 100 kilopascals, and we compress it at constant temperature down to 0.2 cubic meters, and we want the new pressure. Boyle's law says pressure 1 times volume 1 equals pressure 2 times volume 2, so the new pressure is the first pressure times the first volume, divided by the new volume. That's 100 times 0.5, which is 50, divided by 0.2, giving 250 kilopascals. So squeezing the air into less than half the space more than doubles its pressure to 250 kilopascals. Next comes Charles's law, which deals with volume and temperature. At constant pressure, the volume of a gas is directly proportional to its absolute temperature. Heat it, and it expands. Cool it, and it contracts. We write volume over temperature equals a constant, so volume 1 over temperature 1 equals volume 2 over temperature 2. The temperatures absolutely must be in Kelvin, or the ratio comes out wrong. A hot air balloon rising as its air warms and expands is Charles's law made visible. Use it whenever the pressure is being held constant. Let's work 1. We have 0 moles or 20 cubic meters of gas at 300 Kelvin, heated at constant pressure to 350 Kelvin, and we want the new volume. Charles's law gives volume 2 as volume 1 times the new temperature over the old, so 0.020 times 350 over 300. That's 7.0 over 300, which comes to about 0.0233 cubic meters. So warming the gas from 300 to 350 Kelvin expands it from 0.020 to roughly 0.023 cubic meters. Now we bring the gas laws together into a single relationship. The ideal gas law, pressure times volume equals nRT. Here N is the amount of gas in moles, and R is the universal gas constant, 8.314 joules per mole per Kelvin. If you keep pressure in pascals, volume in cubic meters, and temperature in Kelvin, everything comes out in consistent SI units. The great thing is you can find any one of the 4 quantities if you know the other 3. An ideal gas is an idealization, no particle volume, no attractions, but real gases behave very close to it at everyday conditions. It's just the tool for sizing a gas cylinder or an air receiver. Let's use it. We want the pressure of 2.0 moles of gas held in 0.050 cubic meters at 300 Kelvin, taking R as 8.314. The ideal gas law rearranges to pressure equals nRT over V. The top line, nRT, is 2.0 times 8.314 times 300, which is about 4988 joules. Dividing by the volume, 4988 over Sommen-Vesfärdig, gives roughly 99800 pascals, or about 99.8 kilopascals. Reassuringly, that's close to atmospheric pressure. Sometimes pressure, volume, and temperature all change at once, and then we use the combined gas law. Pressure 1 times volume 1 over temperature 1 equals pressure 2 times volume 2 over temperature 2. It's rather elegant because it contains the others. Hold the temperature fixed, and it collapses back to Boyle's law. Hold the pressure fixed, and it becomes Charles's law. So in practice, choose Boyle's when temperature is constant, Charles's when pressure is constant, and the ideal gas law, pressure times volume equals nRT, when you actually know the amount of gas in moles. Let's pause for a quick check. First, which gas law applies when a gas is compressed at constant temperature? Second, why must temperature always be in Kelvin for the gas laws? Third, can you state the ideal gas law and give the SI units of each quantity? And fourth, which mode of heat transfer can travel through a vacuum? Have a think before we press on. Let's move to warming things up and the idea of specific heat capacity. The specific heat capacity, C, is the amount of heat needed to raise 1 kilogram of a substance by 1 Kelvin. The heat transferred is Q equals mc delta T mass times specific heat times the temperature change. Water has a very high specific heat, about 4,886 joules per kilogram per Kelvin, which is why it stores so much heat. Metals have low values, so they heat up and cool down quickly. Delta T is just the temperature change, final minus initial. It's the tool for sizing a coolant flow or an electric water heater. Let's calculate 1. How much heat does it take to raise 2.0 kilograms of water from 20 up to 80 degrees Celsius with C of 4186? First, the temperature change. 80 minus 20 is 60 Kelvin. Then Q equals mc delta T, so 2.0 times 4186 times 60. That's 8072 times 60, which comes to 502320 joules, or about 5.2 kilojoules. So warming those 2 kilograms through 60 degrees needs a little over half a megajoule of heat. Let me introduce enthalpy, which is a measure of the total heat content of a substance at constant pressure. A change in enthalpy is the heat added or removed while the pressure stays constant. We give it the symbol H and write a change as delta H, measured in joules. A positive delta H means heat has been absorbed, a negative one means heat has been released. Engineers lean on enthalpy tables for steam and refrigerants, and it's the quantity underlying the heating and cooling that goes on in boilers and heat exchangers. Let's think about changes of state. Matter can be solid, liquid or gas, depending on how much energy its particles have. Melting takes a solid to a liquid, and freezing reverses it, both at the melting point. Boiling or evaporation takes a liquid to a gas, and condensing brings it back at the boiling point. Here's the surprising part. While a substance is changing state, its temperature holds steady even as you keep adding heat. That heat is busy rearranging the particles rather than raising the temperature, and this hidden heat has a special name, latent heat. So let's meet latent heat properly. Latent heat is the energy needed to change a substance's state without changing its temperature, and we calculate it with Q equals mL, where L is the specific latent heat in joules per kilogram. There are two kinds, the latent heat of fusion, for melting or freezing, about 4,000 joules per kilogram for ice, and the latent heat of vaporization, for boiling or condensing, a much larger 20 to 6,000 joules per kilogram for water. Notice there's no delta T term, because the temperature simply doesn't change. It's what you need for sizing freezers, chillers, and steam plant. Let's work one through. How much heat melts half a kilogram of ice at 0 degrees Celsius into water at 0 degrees, with a latent heat of fusion of 4,000 joules per kilogram? The formula is Q equals mL, so that's 0.50 times 4,000, which is 16,700 joules or 167 kilojoules. And notice all of that heat goes in while the temperature stays fixed at 0 degrees. It's spent entirely on turning solid into liquid. Let's lock in the thermal terms. Specific heat capacity, C, is the heat needed to raise 1 kilogram of a substance by 1 Kelvin, in joules per kilogram per Kelvin. Latent heat is the heat that changes a substance's state without changing its temperature. The latent heat of fusion is the heat per kilogram to melt a solid or freeze a liquid, and the latent heat of vaporization is the heat per kilogram to boil a liquid or condense a gas. And enthalpy, H, is the total heat content of a substance at constant pressure. Time for another check. First, can you write the equation linking heat, mass, specific heat capacity, and temperature change? Second, why does the temperature stay constant during melting even as heat keeps going in? Third, can you calculate the heat needed to melt 1.0 kilogram of ice with a latent heat of 13,34,000 joules per kilogram? And fourth, why does water make such a good coolant compared with a metal? Let's pull the whole outcome together into a method. First, work out what's actually happening, a temperature change, a change of state, or both. If it's a temperature change with no change of state, use Q equals mc delta T. If it's a change of state at constant temperature, use Q equals ml. State the principle you're using and keep every unit in SI. And if it's a gas, first decide which gas law fits the condition that's being held constant. Then, as always, check your answer is sensible in both size and units.